Okay, hello, welcome back. Here we are. We've made it through our first week of online learning and teaching, and we're just going to keep on going. So I hope you all are well. It's kind of sad to talk to a camera instead of our classroom, but we're all going to soldier through and get through all of this and be very excited to be back in the classroom the next time we can be. So anyway, welcome back. Don't forget, we do have a quiz on Wednesday, April 1st. And so this week we are diving into more of Chapter 11. Today we're back to Section 11.2, which we transitioned to last time. Make sure you're checking your Canvas and your emails and Canvas announcements for all of the various things I've been sending you, and WebAssign as well, right? Okay, so here we are. Last time, what did we do? We introduced the concept of Section 11.2, which is really the concept of the rest of the semester for Calc 2. And that is series, or when we say series, we mean infinite series, okay? And what does that mean? It means summing infinitely many numbers. That's the question, right? And so here's your basic notation, right? You're going to sum a bunch of numbers that have some pattern associated with them, or something that they're related by, and so we call them a sub n's, right? And oftentimes we won't even say where we start counting, and again, like we said before, it doesn't really matter. I could say sum of a sub k, sum of a sub I, right? All of these things just mean an infinite sum, and it's only going to be different if I start like putting letters down here, right? So if I say sum n equals 1 to infinity, then that tells me I start counting at n, these guys a sub n's, and that's what we have written out right here, what that means, right? A1 plus A2 plus A3 plus A4 forever, right? Go on and on forever. But this means the exact same thing, right? The sum k equals 1 to infinity of a sub k means the exact same thing. A sub 1 plus a sub 2 plus a sub 3, right? If I use a different letter down here, if I had the sum k equals 1 to infinity of a sub I, that would just mean keep adding a sub I over and over and over again, because I have different subscripts, so I've got to make sure I have the same subscript, right? If I want to start counting somewhere else, then I can start counting somewhere else, and then that's why we might sometimes put in the counter and sometimes not, just to indicate it's an infinite sum. Okay? All right. So let's talk about this notation then, right? So we're summing infinitely many things, and the question is, does it sum to something finite or doesn't it, right? That's the main question, okay? And let's make sure we again understand all of this notation. So this is one way to think about it, right? And we've got to use the dot dot dots. This tells us exactly what we mean mathematically, right? Here we're just saying do this and then keep on going forever, right? But we need a mathematical construct so we can actually deal with something like this. How do we deal with keep on going forever, right? How do you do that in a way that holds water and makes sense, right? When you're just not making rules up and doing whatever you feel like doing, you can't do that, right? And so what does this mean? This notation also means, well, what am I going to do, right? I'm going to add up finitely many things, n things. Whoops, I didn't mean to erase the infinity there. And then I'm going to take a limit as that finitely many things goes to infinity, right? Okay. So here, this notation, sum k equals 1 to n of a sub k, right? This is a finite sum. Yeah, this is a finite sum. Finite means not infinite, right? And so that's just you're adding up n things, and that's something that we can all do, right? Okay? That doesn't take any special power of calculus. This is the calculus, right? Okay, so that's a finite sum of n terms, so let's write that out. It's just a sub 1 plus a sub 2 plus a sub 3, right? Sum plus whole way out till we get to plus, increment the counter to n, a sub n, right? Okay, so that's what this guy's a finite sum. This guy is an infinite sum. What is an infinite sum? It's a limit of a finite sum, right? Good. Okay, so here's it written in short notation, right? But here's it written out. The limit as n goes to infinity of that. And that is something that we need to keep working with, right? And what do we do whenever there's like a thing that takes a lot of space to write out? We give it a new name and a new symbol so we know that we mean that thing. And what is the name and what is the symbol that we give this? We call it S sub n. S sub n is a1 plus a2 plus a3 out to an, right? That is so then that turns this expression, right, into the limit as n goes to infinity of S sub n. Right, so where are we then? What do we really mean when we talk about this guy? The sum n equals 1 to infinity of a sub n is equal to the limit as n goes to infinity of S sub n. So this S sub n is the thing we're going to have to be paying some attention to, right? That is not this guy, right? Okay, they're different. We're going to have to figure out how to compute that. Now notice this finite sum is S sub n, right? That's what this is. a1 plus a2 out through an. This is a shorter way to write it, right? Sum k equals 1 to n of a sub k, right? Okay, so now we've got all of the notation, right? And making sure we understand the different letters. And our question is going to be, well, what is this guy? So, notation, vocab word, what do we call that? What is the new vocab word for that? It's the nth partial sum of that series. It's the nth partial sum. We're summing up part of this series with S sub n. What part? The first n terms. Yes? That's why it's called the nth partial sum of this infinite series. Yes? The sum of the first n terms is Sn. So what does that give us, right? Coming up here, so the terms Sn are the terms in a sequence. Right? Section 11.1. We call that sequence the sequence of partial sums. And we denote it with sequence notation, right? The curly braces, right? Curly braces mean sequence or set with infinitely many elements in it. So Sn is the sequence of partial sums. That's what this is, right? What is in Sn? It's a list of numbers, S1, S2, S3, that goes on forever, right? And there's always a next term. Yeah? Okay. And so in order to determine this sum, we've got to come up with, okay, if we have some terms in a sequence, then we'd have to come up with what is the nth term, what's the pattern, so that we have some nice easy formula to take a limit of, right? Because while this is a formula for Sn, right here and right here, it's not something you can easily take a limit of. It's not a closed form expression, right? We'll need a closed form expression in order to compute that limit, okay? We'll want a closed form expression. This is not closed form because it's sum adding up everything up. We'll want a closed form, like a formula, right? A formula that only involves n, that we can easily take a limit of, just like we were doing in section 11.1, right? We'll want a closed form expression for S of n, which is not what we have so far. We just have summation expressions, okay? All right, so let's go back to our more vocab, right? More vocab, so what do we say, right? We say that the sum n equals 1 to infinity of a sub n converges to s, right? Converges to s, right? If this thing, which is just like, all of that stuff, right? If we kept adding all of that up, what would we get? S. That's kind of the deal, right? So you converge to S. If adding all of the infinitely many things, right, is S, well, what does that mean? How can we say that? What does that really mean? Well, what does that mean? It means that if we take this limit of the nth partial sum, right, then I'm just going to write in Sn here because we know what that's. If this limit of this nth partial sum, this guy we don't have a closed form expression for yet, is S, right? Okay, where S is some real number, right? Where S is like L for us before, right? It's the limit of that sequence. So where S is some real number, right? What do we mean by this? S is a single finite, all real numbers are finite, right? Single finite real number. Yeah? Okay? Okay, so question is, when can we find this S? Not a lot of times, actually. When can we determine that this thing actually sums to something finite? Well, maybe more than that. So that's kind of what we want to talk about. So that's what we say that this guy converges, right? When this limit exists, right? When this limit exists. And so what about when that limit doesn't exist? What do you think we call that? What do we call it? What do you think? I bet you guessed it. We say that the series I used a K. It doesn't really matter, right? Well, I just don't want to confuse you. We'll just write it all in here. N equals 1 to infinity, a sub n, right? We say that the series, this guy diverges. Right, that guy diverges if the limit as n goes to infinity of s sub n diverges, or doesn't exist, right? Okay. Oh, sorry. If this limit does not exist, right? I.e., if the sequence of nth partial sums diverges, right? This sequence, check last section, right? Don't tell me you lost it already, right? Okay? A sequence diverges when the limit of its nth term doesn't exist, right? And a sequence converges when the limit of its nth term has a limit, right? Okay? So just to rewrite what I just said and repeating, right? The series sum n equals 1 to infinity of a sub n converges, right? This is the series, right? The summing everything converges if the sequence of partial sums, right, converges, right? So up here, right, we said it converges, and it also converges to the sum S, and S is actually what Sn converges to. So we could say converges to S if the sequence of partial sums converges to S, right? Okay, adds to S. All right, so let's start taking a look at this sequence of partial sums, okay? Because that's the guy, right? That's the sequence that's important. for us here now for series. We've got to understand that sequence in order to be able to say what's happening with a series. Yeah? All of our work in section 11.1 is what we'll want to put together to try to figure out if that sequence converges or diverges. Okay, so let's write that guy out a little bit, okay? Let's think about what in the world that is. Let me switch colors for a sec. Okay. So here's our infinite series, right? So this guy is our series. We're going to do this in general, and then we're going to do it for some examples in just a little bit. Okay, so that guy's our series. So what is the sequence of partial sums? So the terms in the sequence of partial sums. Okay, well, the first term, S1, is just the first guy, A1, right? And the second term, S2, in the sequence of partial sums, right, over there, would be what? You guys tell me. S2 is the sum of the first two terms of the sequence, right? The sum of the first two terms of the sequence. So what will be? Good. A1 plus A2, right? Yeah? A1 plus A2. That's what's in the S2 spot, right? What's in the S3 spot? The sum of the first three terms of the sequence, right? So if you know what these things mean, they're not just a bunch of, symbols you're writing down. If it's speaking to you, the sum of the first three terms, what is the sum of the first three terms? A1 plus A2 plus A3, right? That's what's really in this spot, yeah? What's S4? Good, you're getting this. A1 plus A2 plus A3 plus A4, right? Yeah? Okay? And so in general then, what is Sn? In our summation, right? Notation, or with just writing them out, I add up until I get to A sub n, which was exactly what we defined S sub n to be, right? The nth partial sum, the sum of the first n terms of my series, yeah? Okay? So, what other things do we want to notice that are going to make our lives work a little bit simpler as we keep moving on? So let's look at this, right? So these are the terms that are in this sequence, right? Okay? Right, so this guy is just A1, right? And this guy is A1 plus A2, right? This guy is A1 plus A2 plus A3, right? Right? Okay. So what else is going to be something useful for us? Maybe I'll do this in red just so that we see it's, well, A1 was S1, right? So S2 is just S1 plus A2, right? Yeah? S1, can you see that? S1 plus A2, right? The previous sum plus the next term, right? What about S3? How could we rewrite that? Well, A1 plus A2, this piece is just S2, right? The previous sum, you already went through the work to figure that guy out. So you already have that part. Those two guys added together is S2, right? Plus A3, right? What about S4? You guys tell me. Good. The previous sum, which is S3, right? Plus A4, right? Okay, let's see if we can continue that idea down here. What about Sn then? Let's make a little more space here for a second. What's in Sn? Well, it's A1 plus A2 plus A3 plus, whoops, that's a 3, dot, 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 right? Go on forever, right? The last term is an. What's the term that came before an? Right, S4, right? What's the term that comes before this guy? Good. A sub n minus 1, right? Yeah? So, if I want to kind of do that exact same thing, what is that? Well, I'm adding up which terms? The first, second, third, up through the n minus first term, right? A sub n minus 1. So this piece is adding a1 up through the n minus first term. What do we call that? Good. That's s sub n minus 1, the n minus first partial term. Partial sum, right? N minus s sub n minus 1 plus the next guy. Yeah? Plus the next guy. Okay. So that's these are all important things that we'll utilize quite a bit. Let me mention just a couple of things. So in this series, right, in this series, we just said that this is the limit as n goes to infinity of s sub n, right? Okay. Why is that? We could keep writing it over and over again, right? Because make sure we understand it. Why? Because what does this mean? In summation notation, it's sum n equals leave myself enough space. It's a limit as n goes to infinity of the finite sum, right? Yeah? And this finite, this, okay, right? We've got to switch letters here, right? Because I've got my n up there. So k equals 1 to n of a sub k. Yeah? That's a1 plus a2 plus a3 out through an, right? That's what we just had there. So this sum is this limit, right? And the question is, does this limit exist, right? Does that limit exist, right? That's going to be our so if the answer is yes, right, then what happens? The series converges. And if the answer is no, then what happens? The series diverges. Right? Okay? If the answer is yes and the series converges, then the question is, can we say what the series converges to? What does it sum to? Right? What is S? Right? If this guy is equal to S, right? If we're up in here, right? Then this limit is some finite number, S, and what is it? Well, that is actually a pretty tricky thing. So, it is actually generally difficult to say what a convergent series sums to. Certainly at this stage of the game for us, okay? It's hard to say what S is. There are two types of series. Two types of series for which we have a process. To determine the actual sum S, okay? That is somewhat friendly. We'll just go with that. Somewhat friendly, ha ha ha, right? Okay? What are the two types of series for which we have a process that's somewhat friendly? To actually do what, right? What is to actually sum the series, when you're told to sum the series, that means find S, right? Sum the series means find the limit, right? So if you're told to sum the series, you kind of know it's got to be one of these two types, because otherwise we're just going to be able to say whether the series converges or diverges, and we're not going to be able to sum it, okay? What are the two types? We're not going to do those both just yet. We're going to just name them, and then we'll come back to them in a little bit, okay? One type is called telescoping. I'm hoping to do that today. Telescoping series. The other type is called geometric series. Maybe that might ring a bell for you for something. We'll talk about what those are. Not this lecture, next one, okay? These guys come up quite a bit. Okay, so, but for now, before we start talking about a couple of types of series for which we actually can sum the series, what we want to do is try to figure out, okay, well, since this sounds a little hard, maybe, like, no, not hard, just like, you know, you just gotta try to keep it all straight, right? Since it sounds a little nutty, right, the convergence piece seems like, okay, well, wait, we can either say it converges, and then we may or may not be able to say what it actually sums to, right? But the divergence piece looks like a little bit simpler, right? If the, you know, if the series diverges, you're just saying, you know, okay, diverges because this limit doesn't exist, right? So let's just work on divergence first, and then we'll come back to convergence. Does that sound good? Yeah? That seems a little bit simpler. Yeah? So I'm going to do this, you won't be at all surprised, a little bit out of order from the way that your book does things, but it's nice, I think, to focus on this particular critically important result that you are going to carry with you for the rest of the semester before we dive into subtleties of the convergence and finding sums, okay? So our goal first is to be like, well, wouldn't it be cool, right? Wouldn't it be cool if there was some like nice, very simple test that would allow us to conclude, no way, man, this series diverges. It has no hope of adding up, you know, adding up these infinitely many terms. It has no hope of actually adding to anything finite, right? That limit doesn't exist. There's no way. Wouldn't it be nice if there was a nice, simple test that would let us conclude that without having to go through all that partial sum stuff and figuring out like some other new formula? Wouldn't that be awesome? That would just be like a world too good to be true, right? Okay? Well, whoops, today's your lucky day. Lo and behold, we have such a theorem. Okay, so that's what we're going to start with for us, our very important result. Okay. Okay, we'll carry this with you the rest of chapter 11. And we'll just write that. Wouldn't it be nice if there was a simple test to determine if a series, some piece of it, might diverge. Right? Wouldn't that be nice? Well, there is a very important result. Anybody want to guess what the name of this result is called? It's a test for divergence. Good. The divergence test. The divergence test, okay? It's a theorem. Ooh, that's exciting. must mean we're going to prove it. And it's actually so far, so you know, it's theorem 7 in your book. Okay. Page 713, just so you're aware. Okay. Because like I said, we're doing this a little out of order. Okay. Before I write down what the divergence test is, what is the only thing you can ever conclude from applying the divergence test? What do you think? Divergence. Good. Will you ever be like, this series converges by the divergence test? No. Never. Right? Never. Okay? Keep that in your mind. Okay? All right. What does the divergence test say? Right? The divergence test says, let's consider the series. So now I'm going to just stop writing the subscript and superscript n equals 1 to infinity, just because, you know, it's just extra writing and it's going to take up too much time. It really doesn't even matter where we start summing, okay? We could start summing from 30 to infinity, right? If the series is going to diverge, it's going to diverge. If it's going to converge, it's going to converge. But where you start summing is going to affect the actual sum if it does converge, right? Okay? All right. So anyway, here we go. So consider a series, sum n, okay? Here's what the divergence test says, okay? If the limit as n goes to infinity of a sub n, right? The nth term in here, the generating term, the one that's going to be staring right at you. We're going to do an example in just a sec, right? In a problem, if that limit is not 0, okay? If that limit is not 0, then that series diverges. Ooh. That is a crazy awesome result. A crazy awesome result. Let's do a quick example, okay? So here's an example. This is exercise 36 in section 11.2. Okay, so here's the sum. Sum n equals 1 to infinity of 1 over 1 plus 2/3 to the n. Oh, that's just looking kind of crazy, right? Okay, that's looking kind of crazy. The question is, does this series converge or diverge? Does the series converge or diverge? Does the series converge or diverge? I'll let you think about it for a sec, see what you think. Well, why are we doing this problem? As an example of our awesome test, which we haven't proven yet, which we're about to do here in just a minute. Okay? So, what does this guy say? It says, if I'm trying to test a series, sum of some set of terms, a sub n, so here's your a sub n's now, right? What do I need to do? I just need to look at the limit as n goes to infinity of the generating thing. I don't have to start computing all those partial sums, so let's do that. Well, let's consider the limit as n goes to infinity of 1 over 1 plus 2/3 to the n. What is that limit? Okay, well, I think you got it. We'll see. Limit as n goes to infinity of 1, the numerator, right, is just 1. Good, right? Limit of a constant is the constant, right? Limit tools, limit rules from last section. Now let's look at this guy, right? So we know it's not going to be indeterminate. We're going to be able to determine, okay, limit as n goes to infinity, the denominator, so again, I've got the limit of 1, right? Plus, what is the limit, right? Sum rule, right? Quotient rule, sum rule. For limits, limit as n goes to infinity of 2/3 to the n. What is the limit as n goes to infinity of 2/3 to the n? Did you see that in a previous lecture? Did we prove it in general for numbers are in absolute value less than 1, right? Any number between -1 and 1, and I raise it to the n, what happens to that limit? As n goes to infinity at 2/3 to the n, what is that limit? Good, this guy goes to 0, right? Yeah? Okay, awesome. That goes to 0, so that's 1 plus 1 over 0, 1 over 1 plus 0, which is 1. What do we conclude? Good. What are we trying to do? We're testing the series for convergence or divergence, right? What does the divergence test say for series? It says if that limit is not 0, I got 1, 1 is not 0. I highly encourage you to write this, right? So that you remember what this test is telling you and why. I got 1 from doing the limit of my a sub n, right? Okay, this guy is my a sub n. 1 is not 0, therefore what can I say? By the divergence test, this series does what? It's the only conclusion you can come with a divergence. Diverges. This series diverges, right? Let's recap. Let's write that again. So, right, the sum n equals 1 to infinity of 1 over 1 plus 2/3 to the n diverges. That does not add. This series, if I start adding these numbers up, 1 over 1 plus 2/3 plus 1 over 1 plus 2/3 squared plus 1 over 1 plus 2/3 cubed, right? If I start adding up all those numbers, right, that is not going to converge to something finite. This diverges. Yeah? By the divergence test. This is a pretty powerful test, right? That's it. You're done. Okay? Now, hold on. Before we go anywhere, let's recall what if instead, right, what if the question were this? What if the question was back in 11.1 about the sequence? I'm going to write the word here, but you don't even need the word written there, because if you saw, whoops, that doesn't even look like a curly bracey. If you saw a curly brace, and then I said, what about this guy? Does that sequence converge, right? Now, by taking this limit, we would still take that same limit to determine if the sequence converges, and we got 1 for that limit, so does this sequence converge? Yes, indeed it does. The sequence converges to 1, right? What is the sequence? This sequence converges to 1, right, as n goes to infinity, right? Because that limit goes to 1, right? So remember, the sequence is just the dots, right? Do those dots tend to a specific number as n goes off to infinity? Here we're adding up all the dots, right? Okay? Adding up all the dots diverges. The dots converge. Yes? So don't confuse what it means, right, to converge and diverge between sequences and series. That's going to be super important, okay? So this sequence converges. Right? And converges to 1. All right. So now that we've got that idea, let's start talking about how we're going to do this proof. Yeah? Okay? So we can see, it would be nice, we can kind of call this guy, he's a kick-out test. Right? It's a kick-out test. Okay? That's like, okay, we're going to try to kick this guy out. Does he converge or diverge? Nope. Kicked out by the divergence test, right? Divergence test kicked him out. Why? Because the limit of the nth term was 1, which isn't 0. All right, so let's go and erase this and now see how we're going to prove this theorem. Okay. So, this guy, right, this theorem, we've talked about quite a bit, has the form if A, then B, right? If A is true, then B is true, right? Okay? This is called the direct statement. And the direct statement is logically equivalent. Those of you in Math 245 should be getting super excited right now. Is logically equivalent to what? What is it called, guys? No worries if you don't know this. What's called the contrapositive of the statement. The contrapositive. Contrapositive. Okay? This statement is logically equivalent to the contrapositive of this statement. What is the contrapositive? Well, to write the contrapositive of a statement, leave a little space there, right? It's still an if-then statement, okay? And what do I do? You guys in 245? Good. Right? If A then B is equivalent to, if I take B and I negate it, so if not B, and I put it here after the if, right? So negate this guy and it comes after the if. And then what do you think we do with this? Negate it and put it after the then, right? If not B, then not A, okay? These two statements are logically equivalent, which means they are exactly the same statement, okay? So sometimes it's super nice to rewrite an if-then statement in its contrapositive form because it's easier to prove, and it also gives us just something else to think about, a different way to think about the same thing, okay? So let's write the contrapositive of this. So the contrapositive of the divergence test is, okay, so what's in the A spot for the divergence test? That this guy is not 0. And what's in the B spot? That series diverges, right? Okay? So the contrapositive of the divergence test is if, okay, so what does this say to do? Take the B guy and negate it. So what does it mean if a series does not diverge? Good. Not diverging is good. Converging, right? So if the series converges, then, writing the contrapositive, what do? We do not A, right? How do we negate this statement? What has to be true about the limit as n goes to infinity, base of n, right? If that limit is not 0, and we want it to not be not 0, not 0 is 0. Good. Okay? So the statement here in blue is the contrapositive of the divergence test, right? They both say or mean the exact same thing. They both are logically equivalent to each other, right? And so this version is going to be easier for us to prove than that version. Now let's hold on here just a sec before we dive into this, right? What does this contrapositive say? If a series converges, then its limit of its generating term, right, the AN guy, had to be 0, right? If that limit's not 0, no chance it diverges. But if that limit is 0, does that mean the series converges? Absolutely not, right? Okay? If that limit is 0, if we take this limit and the limit is 0, well then we know nothing, right? Okay? We know nothing. Yeah? Okay? We know that the series could converge, it could diverge. We have to come up with some other test to try. Yeah? Okay. So, let's try to prove this theorem. Okay? What this does tell us is that if we know a series converges, then we're going to know that its nth term has to go to 0. Okay? But you can't use this as a test for convergence, right? So it's not as simple as that. All you can do is use this as a test for divergence. Done. Period. All right. So let's see, how are we going to prove this thing, okay? Well, so let's recall what we just had. Let's prove. Let's prove the contrapositive. And the cool thing about logically equivalent statements, right? If we prove the contrapositive, we've proved the original statement, right? So if we prove this, we prove that. Yeah, that's pretty awesome. Let's prove the contrapositive of the divergence test, which proves the divergence test. Okay, so we're going to prove this statement. So, what do we want to do? Okay, well, so let's say proof. Okay, well, I get to start with what I've got here, right? We're allowed to know that this series converges. If this is true, then we've got to show that is true, right? Okay, so we're going to say, let it be true that that series converges, right? That's what we're going to start with. Okay, well now we're going to have to find a way to get this guy, this term in here, a sub n, so that we can think about that limit, okay? So let's come over here to the side for a second. Recall, remember when we were doing this, S1 is A1, right? S2 is A1 plus A2, but that's really S1 plus A2, right? Yeah, right? We'll do one more. S3 is A1 plus A2 plus A3, but that's really good. That's really S2 plus A3, right? Okay, and so then we were down here and we said Sn, right? Okay, let's skip this piece. It's the sum A1 plus A2 up through, right? What did we say that was over here, right? Good. It was the previous sum plus the next term, right? S3 is the previous sum S2 plus the next term A3. Was the previous sum Sn minus 1 plus An, right? Good. And so now what's another way to write An? Well, how could I solve this equation for An? Solve for An, do what? Subtract S sub n minus 1, right? So Sn minus Sn minus 1 is An, right? Okay? So now we've got a cool expression for An, and the nice thing about this cool expression for An is it involves what it means for this guy to converge. Yeah? Okay? So let's let this guy converge. And so we'll just, let's put in our letters now, or our subscripts now. So we'll say if this, we'll just look at the sum n equals 1 to infinity here. So let's let this guy converge, okay? So what does it mean to converge? So, well, the limit as n goes to infinity, right, of the sum k equals 1 to n of a sub k, right, well, equals, yeah, so equals s. I think I'm gonna, I should have probably did this in a different order, but we'll go with it. Okay. So that's what it means for this guy to converge, right? But what is this expression right here? What is that expression right there? I.e. the limit as n goes to infinity of, what is that guy? S sub n. All right? S sub n is the nth partial sum. S sub n is s, right? Okay? So now, I wish I had a bigger board, but I'm just going to come over here and erase this piece because we've already got that part down, and this was the part that we needed, okay? So this is what comes from knowing that guy converges, right? We know he converges, therefore it sums to some number s. What does that mean? The limit of the nth partial sum is s. That's what it means for a series to converge. Okay, now let's see if we can look at this limit as n goes to infinity of an and see if there's any way we can come up with 0, okay? So let's consider the limit as n goes to infinity of a sub n, right? Well, by our formula right here, that's the same as the limit as n goes to infinity of s sub n minus s sub n minus 1, right? From what we just did right there. Now we have limit tools, right? Limit rules. This is a limit of a difference. What does that mean? That means, well, that's the limit of a difference is the difference of the limits. Yeah? Nice? We just talked about what is the limit as n goes to infinity of s sub n. What does that equal? Good, this guy s, what the series sums to, because we know that guy converges, right? So he sums to something finite. S minus, well, this guy, the limit as n goes to infinity of s sub n minus 1. So that's what we don't know what that is. So what is that guy? Let's figure that out. Yeah? If we can put that in there, then we're about done with this proof. So I'm just going to erase this piece up here because I'm going to leave the divergence test up there. And we're going to come up there. Okay? So, but you can just continue right down on your paper, right? But what is s sub n minus 1? What does that mean, right? It means I just add a1 plus a2 out to, I stop at a sub n minus 1, right? How do I do that in summation notation? I'll do it up here. That's the sum, k equals 1 to n minus 1 of a sub k, right? Yeah? So the limit as n goes to infinity of s sub n minus 1 is the limit as n goes to infinity of the summation. Yeah? Okay? So if n is going to infinity, tell me, where is n minus 1 going? If n goes to infinity, where's n minus 1 going? Infinity, right? Yeah, not infinity minus 1, right? No such thing, yeah? If n's growing large without bound, n minus 1 is growing large without bound. So what is this equivalent to? This is equivalent to the sum k equals 1 to infinity of a sub k. Yes? Because this guy's going to infinity. And therefore, the limit as n goes to infinity of s sub n minus 1 is also the sum of the series, which we said was s. Yes? And so, what can we put in here? What is that guy? Also s. What is s minus s? Woohoo! 0, which is what we were trying to prove, right? So that proves that if a series converges, right, then the limit of its nth term had to have gone to 0, which, when we look at the contrapositive, gives us a test for what? Divergence, and divergence only, right? A test for divergence and divergence only. Okay? That was awesome. That was fun. That was such cool things, lots of interesting things in there. You know, if the limit of the nth term, the nth partial sum, and the limit of the n minus first partial sum are going to the same thing if you've got a series that converges. Let's write down one more thing before we move on, and we're going to do more examples. Let's write this in red, okay? If, I want all these three things right in nice one place. If the limit as n goes to infinity of a sub n is equal to 0, then what? What do we know? What do we know? No. Nothing. Right? Nothing, right? Nothing. Yeah? We got that, right? The converse of this statement is not true, right? If the limit as n goes to infinity of a sub n is equal to 0, then a series could converge or diverge. We know nothing, right? No thing. We need another test. Our kick-out test, which is the divergence test, didn't work, and we need another test and we're sad, right? Remember, if that limit is 0, 0 means you know what? Nothing. 0, nothing, right? Equals 0, nothing. If something equals 0, you have nothing, right? Right? Are we good? Okay, divergence test, limit not 0, diverges. Only thing that can be concluded, divergence from the divergence test. Yeah? Kick-out test. Okay, so let's go do a couple more examples now that we understand the theory behind all of this. And let's see, where am I now? Oh, good. Okay. Let's go do another example. Okay? So, we're kind of sitting there hoping that like every series diverges, right? Because then we would never have to find the sequence of partial sums S sub n, right? But you know that's not going to happen, okay? So, but you do want to just try testing. Never lose sight of thinking about the divergence test when you are testing series, because it may be that if you would have thought about that to begin with, you would have easily been able to kick that series out and not gone through a bunch of headache of trying a whole bunch of other series tests that are going to be coming soon, right? The divergence test never goes away. That guy is important the entire rest of the semester. Okay, so let's do an example. Let's go back to our 11.2 number 27, okay? We ended with this one, I believe. Whoops. 11.2, number 27. Remember, they gave us this one, and we're just not even following the directions. We're just doing our own thing. This one was 1/3 plus 1/6 plus 1/9, right? Plus one, or sorry, yeah. Is that what I'm doing? No, right? I was saying plus, and I'm writing a sequence, right? I'm thinking sequences and not series. Okay, good. Let's see how easy it is to, this is 11.2, number 27, right? Which is going to be 1/3 plus 1/6 plus, right? Not the sequence where I was listing out the terms, right? Okay, as with commas and set notation, right? Instead, we're summing, yeah? And what did we already do? We already came up with a formula, right? This is what we did last time, is we said, oh, let's come up with a formula, n equals 1 to infinity. What was the formula for the generating term, right? Because they just gave it to us like this, so we didn't have an a sub n sitting here. You guys remember? Good. 1/3n. That was our guy. And we said, okay, well, think about what do you think? If you add these guys all up, does it add to something finite? Okay. And we did some of the first partial sums. You can go back and take a look at the first several partial sums. But let's just see what the divergence test would tell us. So can we use the divergence test? What would I do for the divergence test? I would look at the limit, right, as n goes to infinity, right, of, right, this guy is my a sub n, right, n equals 1 to infinity of a n, right? So that's what I do. I look at the limit of that guy, 1/3n. What is the limit as n goes to infinity of 1/3n? Good. Constant over something getting huge. Can't compete at all, right? Constant, something getting huge, goes over something getting huge, goes to 0. Good. What can I say? Did I trick you? Did we forget that quick? Maybe? I don't think so. I think you were right on it. I think you just screamed, nothing, right? Okay, we know nothing. We know nothing, right? This series, right? This summation, 1 over 3 to the n, 1 over 3n, could converge or diverge. We don't know yet. Could converge or diverge. We need another test. We're going to get one next section. Okay, that's when we're going to deal with this series. But, so, stay tuned. You can continue to take your wild guess and decide whether or not you think adding those things up would add to something finite. Okay? So that's one of the cases where you get 0, you're like, oh, okay, can't do anything, I got 0. Okay, so now what? One more time, just contrasting with sequences, right? What about the sequence? What about the sequence 1 over 3n? Does that sequence converge? Yeah, right? The sequence converges to 0, right? Yeah? The sequence converges to 0. Why? Because that limit is 0, right? That's how you determine whether a sequence converges, right? This is 11.1, right? The series, we have no idea at this stage. Okay. All right. Let us see. So what about these other tests? Well, there's more than just one other test. There's lots of other tests. That's what the rest of the semester is kind of all about. Okay. Okay, so now where are we? Let's go talk about a little bit with convergence now, right? Our telescoping sums. Let's see if we can do some of that. All right, I'm going to erase now. Yeah? So now we have our favorite first thought test, our kick-out test, divergence test. That's our buddy. We hope that we take a limit of the nth term of a series, the generating term, the term that generates the series, not have to compute the partial sums. And we hope beyond hope that the limit is not 0, because if that's the case, the limit is any number that's not 0, then we can immediately conclude divergence. That's the only thing that comes from a divergence test. Okay, but what about if we're going for convergence and actually trying to find the sum? So let's talk about one of the 2 types of series where we have a reasonable path toward finding the sum. Of a convergent series. Right? Okay. So we're going to first go with the telescoping series. We'll do geometric next lecture. Okay? Okay, so let's just, what does this even mean? Maybe we should just start with perhaps an example. Okay? So again, when the directions say find the sum if it converges, then you know it's got to be either telescoping or geometric, because pretty much anything else you're not going to be able to find the sum for, not for a really long time. Okay, so let's look at particular example. So let's look at problem number 44. So first of all, well, let's just do problem number 44. This is 11.2. Okay, number 44. Okay, so what do we have? Here's the sum. N equals 1 to infinity of the natural log of n over n plus 1. Okay? All right. So the question is, right, does this converge? Does the series converge or diverge? If it converges, find the sum. Right? That's the question. Okay, so what are we going to try first? Divergence test, right? Okay. Well, the divergence test, kick out, right? Divergence test is a kick out test, right? Kick out. It's a kick out test. That's all it can do, right? Will it work? Will we be able to kick this guy out and say, nope, no chance, it diverges? Well, what we need to do, we would take the limit, the divergence test said take the limit as n goes to infinity of our guy sitting there that generates n over n plus 1, right? Don't have to think about anything, just take the limit. Well, I've got the limit of the natural log of stuff, right? Since natural log is continuous as long as our argument is positive, right? Which it is. Then we've got this limit is the natural log of the limit, right? Of this stuff, right? We've used that idea in several different types of problems. The limit of the natural log is the natural log of the limit. And so let's see, what do we got here? We've got the limit as n goes to infinity of n over n plus 1. Well, that's infinity over infinity, right? So that's in indeterminate form. So you might, be already guessing what that limit is, but let's do the process. What do we do to be able to evaluate this limit? We want to divide by the highest power in the denominator of n, right? Okay. So that would be 1. And so my natural log is still on the outside there. And now I'm going to turn this limit into a limit I can actually do. So that's the limit as n goes to infinity of, divide everything by n. So what's n over n? Good, 1. Divide this guy by n. What's n over n? Good, 1, right? And then divide this guy by n, 1 over n, right? Are we good there? Hopefully you understand where that came from. Yeah? So this becomes the natural log of the limit as n goes to infinity of this expression. We love this expression, right? Because what do we have? The numerator's a constant, yeah? Numerator's a constant. We no longer have infinity over infinity. It's not in a determinate form anymore. This limit is completely determinate. We now can determine it, right? And what do we have? We've got our natural log on the outside, right? The limit of the numerator, limit of a constant is a constant, right? That's our constant rule for limits. So we've got a 1 up there. This guy is 1, right? The limit of 1 is 1. Some rule going on, yeah, all those fun rules. What does 1 over n go to as n goes to infinity? Seems like these things are going to come up a lot, right? So these are things we probably want to have down pat. 1 over something growing huge, right, is going to 0, right? Okay? 1 pizza, infinitely many people in your household, nobody's getting any pizza. All right, so what do we have? We've got the natural log of 1. Oh, good, right? What is the natural log of 1? Good, you guys know it. Okay, it's 0, so now we're sad. Why are we sad? The divergence test tells us nothing, right? Tells us nothing. Right? That means we have to do work, right? Divergence test didn't kick this guy out, now we have to do some work. All right, so what's the work we have to do? Well, we got nothing now except for the actual definition of what it means to sum this series, right? But this guy is kind of nice for us, and just knowing something about telescoping sums, you might rewrite this guy because you know a rule about natural log of a over b, right? So if we rewrote this guy, sum n equals 1 to infinity, natural log of n over n plus 1, right? What is the natural log of a over b? Good, the natural log of a minus the natural log of b. So what should I write? The sum of natural log of, good, n, I'll put in parentheses there to make it make more sense, minus the natural log of, good, n plus 1. So that's algebraically equivalent. I didn't do anything crazy there. That's just natural log algebra, right? But that's just going to make our lives a little bit simpler. So this guy's our an, right? He's our a sub n. Yeah? Sum an. Yeah? And so now what do we have to do? Well, the only thing we can do is start writing down partial sums and see if we can come up with a formula for the nth partial sum. Yeah? Okay. Just wanted to make sure that actually started counting at 1. So let's go here. So what do we have? What is S1? Well, S1 is A1, right? S1 is when you put a 1 in for n, right? So what do we have here? Because we're starting counting at n equals 1, right? Our first term of this series will be when n is 1. So you got to pay a little bit of attention to where it starts counting, okay? Some problems you don't start counting at n equals 1, but this one does. And so we have the natural log of 1 minus the natural log of 2, right? What did you just tell me the natural log of 1 is, though? Good. 0. So that's minus the natural log of 2. Yes? Are we good? All right, now let's look at S2. What's S2? Well, S2 is this previous sum minus the natural log of 2, right? The previous sum, S1, plus the next term when n is 2, right? A sub 2. What is a sub 2? I'm going to have plus natural log of 2 minus natural log of 2 plus 1, 3. Yeah? A1 plus A2. When n is 2, I get that. Make sense? But what happens here? Hey, wait. Woohoo! Look at that. What am I left with? Minus natural log of 3, right? What's S3? Okay. Well, S3 is the previous sum, S2. What was S2? Minus natural log of 3, yeah? Plus the next term, the n equals 3 term. When n is 3, what do I get? Natural log of 3 minus natural log of, good, 4. So what do I have? I have a minus natural log of 3 plus a natural log of 3. What am I left with? Excellent, a minus natural log of 4, right? You getting this? Should we do one more? You got the idea? Let's do one more. S4 is what? The previous sum, S3, which was minus natural log of 4, plus the next term, the term when n is 4 for us, that will be natural log of 4 minus natural log of, good, 5. What happens here? These guys cancel. What am I left with? Minus natural log of 5. Yeah? What's my goal? My goal is come up with a formula for Sn so that I can take a closed form formula for Sn so that I can take a limit of Sn, right? In order to determine what happens to this series. What does it sum to if it converges, or does it diverge? Yeah? Okay, do you see a relationship, right? What's the deal, right? When I have S1, I've got minus natural log of 2. When I have S2, I've got minus natural log of 3. S3 minus natural log of 4. There's a clear pattern here, right? This number is related to that number, how? Or really, that number is related to this number, how? This number is 1 more than that number. This number is 1 more than that number, right? This number is 1 more than that number. So what's our guess for Sn? You guys tell me. We got our minus natural log out there. 1 more than that number is, good. 1 more than n is n plus 1. So this is our formula for Sn. Now, if we were in Math 245, right, we would like to do something like math induction and prove things, but we're not going to do that, right? We're going to just go with our formula and say, hey, we found a pattern. So, you know, you don't have to like freak out now and worry. And so, oh, maybe I should just leave that there for right now. So what did we just discover, right? This limit, right, or this series, right, is equal to what? It equals the limit as n goes to infinity of its nth partial sum, right? That's what we started this whole thing off with today, and talked about at the end last time as well. So what did we just discover now through this work? That the nth partial sum is the limit as n goes to infinity of minus the natural log of n plus 1, right? Yeah? Well, you guys tell me, minus is going to come along for the ride, right? Minus is a -1 constant multiple, right? So we can kind of pull that guy out. And then we've got the limit as n goes to infinity, natural log of stuff, right? Tell me, where is the argument of natural log going? N plus 1 is going where as n goes to infinity? Good. This guy, n plus 1, is growing without bound. The argument of natural log is growing without bound, right, as n goes to infinity. What's the range of natural log? Right, as x goes off to infinity, where does natural log of x go? Good. It grows unbounded, right? Okay, it grows unbounded. Pretty slow, but still grows unbounded, right? And so what's happening to this guy? This whole piece is going off to where? To infinity, growing unbounded positive. But we got our minus out here, right? So what's happening? This guy is growing unbounded negative. What does that mean we can say about this series? This series diverges, right? Okay, this limit does not exist, right? Since that limit does not exist, then this series diverges. This series diverges. Right? So how crazy is that, right? The series diverged, but the divergence test didn't tell us anything, right? Does that make sense? Are we all good there? Okay. This guy diverges. Why do they call it a telescoping sum? Because for this problem, we use rules of algebra for natural log, for logarithms, to kind of make the partial sums kind of collapse in on each other so that stuff would cancel, right? And that's kind of the whole idea of telescoping sums, is find a way to manipulate your partial sums so that you can see a bunch of stuff canceling and then you're just left with something much simpler. We're going to do another example. I know you're happy about that. Okay, so here we go. Here's another example. Oops, sorry about my squeaky whiteboard. There we go. A little bit better. Okay, so there's plenty of examples in your book as well, so make sure you read, right? I'm not going to repeat that because you have that there. See example 8 in your book as well for another telescoping sum examples. That is going to help you do number 43, which is one of your homework problems, okay? Okay? Let's now do one more example. Let's look at number 46. Switch to green. Hopefully you can see green, just to switch it up a little bit. 11.2, number 46. Okay. Now we have some n equals 4 to infinity of 1 over the square root of n minus 1 over the square root of n plus 1. Okay? So this is our sum right, n equals 4 to infinity, right, of a sub n. What is a sub n? All of this stuff is a sub n. Yeah? Okay? Now notice here we start counting at 4, right? Okay? And so what does that mean, right? Our first term is what? Good. A sub 4 plus then some a sub 5 plus a sub 6, right? Plus a sub 7. On and on forever. Yeah? So if we had started counting at 1, we would start, it would be a1, right? a1 would be 1 over 1, right? Minus 1 over the square root of 2, right? Okay? So if we start counting at 1 or start counting at 4, it's not going to make any difference as to whether or not this series converges, because starting counting at 1, you would just have n equals 1, 2, and 3, right? 3 extra terms that are finite that you would add on, right? Okay? And so if the sum from 8, 4 on converges, then the sum from n equals 1, right, will converge, as long as this stuff isn't unbounded when n is 1, 2, or 3, right? And so convergence or divergence is going to be the same no matter where we start. So eventually, when we stop asking for the sum, we'll even just stop even writing this, right? But if we want the sum, then where you start counting is going to make a difference, right? It's going to change the sum, the actual what this sums to, but not whether or not it converges, right? So you got to pay attention when we're trying to find the sum. Okay, so let's look at this one, okay? So let's just dive in here and start to, first of all, will the divergence test help us here? Okay, let's just see. Let's just see. Divergence test. Okay. Right, does it help? Okay, remember it's a kick-out test. We would do the limit as n goes to infinity of 1 over the square root of n minus 1 over the square root of n plus 1. Right? If n's going to infinity, where's the square root of n going? Also infinity, right? The range of the square root function grows unbounded as well, right? Denominator is blowing up, constant on top, 1 over something blow it up, 0, right? Same thing here, yeah? 0 minus 0, 0. Does the divergence test help? No, nothing, right? Does not help, right? The divergence test does not help, okay? All right, so you got to keep going, right? You got to find something else. So the only something else that we have right now is computing the nth partial sums. Okay, so let's start talking about, what's our first partial sum, S1. The first partial sum is the first term in the series, which in this case is just A4, right? Does that make sense? Okay, so our first partial sum is when we're plugging, it's A4 for us now, right? It's just the first term in the series. We plug 4 in for n, so what do we get, right? When we plug 4 in for n, we get 1 over the square root of 4 minus 1 over the square root of 5, yeah? Okay, which, if you want, may or may not be useful to simplify that. What is the square root of 4? 2, good, 1/2 minus 1 over the square root of 5, yeah? Good, okay? That's S1. Okay, so what's S2? S2, right, is going to be, right, A4 plus A5, the sum of the first two terms, right, which is just, right, S1 plus A5, right, okay, so what was S1, right, it's 1/2 minus 1 over root 5, now let's add A5, right, S1 was that, let's add A5, A5 is when I plug a 5 in for this, right, so what am I going to get, plus 1 over root 5 minus 1 over root 6. Ooh, we're seeing something else happen again, right? Same deal, right? Minus 1 over root 5 and plus 1 over root 5 cancel. So these are already set up for you to kind of have this nice thing cancellation happen. Let's do one more, S3. What is that? It's our previous sum plus the next term. What's the next term? It's going to be A6, right? The third term. S3 is the sum of the first 3 terms, right? Okay. So what is that? We've got 1/2 here. We've got our minus 1 over root 6. That's what was left in S2. And then what? We're going to add on a sub 6, which is plug in a 6 everywhere you see an n. So what have we got? 1 over root 6 minus 1 over root 7. Yeah? Well, now what? Beautiful. These guys cancel. What am I left with? Right? 1/2 minus 1 over root 7. Yeah? So let's see if we can come up with a I didn't have enough space here to write this, right? Can we come up with a formula for S sub n? Well, let's see. We got S1 is 1/2 minus 1 over root 5. S2 is 1/2 minus 1 over root 6. S3 is 1/2 minus 1 over root 7. The 1/2 looks like a constant, right? Okay? So maybe we'll guess it's 1/2 minus 1 over the square root of something. Yeah? And what's the relationship between these guys? Okay? So I got a 5 here when I have a 1 there, right? And I've got a 6 there when I have a 2 there. And I have a 7 here when I have a 3 there. Yeah? This number is always 4 more than that number. So what do I have? 1/2 over the square root of n plus 4. Does that make sense? Yeah? Okay. Here's my S sub n. What do I do with it now? Well, this guy is the limit as n goes to infinity of S sub n, right? So that's the limit as n goes to infinity of 1/2 minus 1 over the square root of n plus 4. So can we find the sum of this series? Yes, indeed we can, right? What is it? What's the limit as n goes to infinity of 1/2? Beautiful, 1/2. This is a limit of a difference, is the difference of the limits, right? Minus, what is the limit as n goes to infinity of 1 over root n plus 4? Good, the denominator's going to infinity. This 1 over something blowing up is going to 0, right? 1/2. That's the sum of this series. If we add that all up, we get 1/2. Okay, and so this series converges. Therefore, this series converges to 1/2. 1/2 is S for this problem, right? Now remember what was right here before I erased it. We tried the divergence test and we got a limit of 0, right? And so it told us nothing as well. So now we've seen here is a place where we got a limit of 0, and this time we have a convergent series, whereas the previous example we had a limit of 0 for the nth term and we had a divergent series. So that ought to also convince you that if the limit of the nth term is 0, that tells you absolutely nothing about what the series is going to do, converge or diverge. And that's why we have a whole rest of the semester, right? Otherwise, it'd be so easy and the game would be over. Yeah? Okay, let's talk a minute about that homework problem and just kind of close it all up here. And then we'll open up our next lecture with section 11.2, clean up pretty much the rest of 11.2 with geometric series and algebraic properties of series. So let's see. Oh, I thought about maybe doing that one other fun problem too. Well, let's see. Let's just erase this for now. So one nice thing that happened about these two problems that I just did for you on telescoping series is they already were written in a form, the nth term, or easily written with the natural log one, into something where I subtracted one thing from another thing, right? And that's what set up that canceling that allowed us to see how things cancel and come up with a formula. It's not always quite that simple. Sometimes you have to write out a few more terms, not simplify things until you eventually see the pattern come in. This one in example 8 in your book will help you with number 43. So let me just write down what that one is, number 43. So this one is a homework problem for you. And this guy looks like this. The sum n equals 2 to infinity of 2 over n squared minus 1, right? And you may say, well, that looks nothing like the ones you've just done. Not 8. Goodness, I can. Infinity, okay, a little bit better. Clearly was a little bit sideways on that. Example 8 will help you with this one. This one doesn't at all have a nice little setup where you already have like a subtraction kind of going on to help things sort of cancel and then telescope in on themselves, right? So that you're only kind of left with the beginning and the end. That's kind of the deal. Okay? Well, let's look at this guy, right? This is our a sub n, the sum n equals 2 to infinity of a sub n, right? So your a sub n is 2 over n squared minus 1. And I really wish I could write that, maybe as, one thing minus something else, but gee, do we have a method where we could, like, take this fraction and maybe write this fraction into 2 parts that might make up this final common denominator fraction that we would use with integration? Some of you are out there yelling it. Okay, what do we want to compute in order to turn this an into something that might have the chance of telescoping sums? I heard it. PFD, right? Partial fraction decomposition, right? And in order to first, in order to get a partial fraction decomposition, we first have to do what with this denominator? Good, factor it, n plus 1 times n minus 1, right? Okay, and then the partial fraction decomposition would be, what is the partial fraction decomposition of, I have 2 different non-repeated linear terms, right? So that's going to be in, good, constant a over n plus 1. Woo-hoo! You thought that was gone away, right? Ha ha, here it comes, right? Plus a b over n minus 1, right? So here's the partial fraction decomposition. Now you've got to determine a and b, right? And by recreating the fraction, right, doing what we did before with integration when we use partial fraction decomposition, determine a and b, and then replace this guy, right, with this guy, and then start putting in your partial sums. So this guy starts counting at 2, right, so S1 will just be A2, right, okay. So this guy's, right, A2 plus A3 plus A4, right, right. But instead of the an being 2 over n squared minus 1, you're going to use, whenever you use the partial fraction decomposition after you determine what the a and the b are, okay? And the a and the b ought to be opposite sign so that things cancel, right? That's kind of the deal. Okay, so that's just a heads up about that problem. That's pretty much the other types of problems is we look at things like that. Okay, I really have no idea how long this is at this stage. I don't have my phone, and so I think I'm just going to do one more example just because it's, it's sort of fun, and it will help me also help you solidify a little bit more work with factorials, okay? You guys can always take a break and pause for however much time you need, right? Okay, so last example. Maybe I should take a quick drink. Maybe that should tell me it's time to quit, but let's just do one more example. This is number 91 in 11.2. Maybe I won't do all of it, I'll just get you started. Okay, so here's the sum n equals 1 to infinity of n over n plus 1 factorial, okay? And our question is, well, what do we do with that, right? Does this converge or diverge? Can we try to come up with what is actually happening here? Well, what is this factorial thing? Well, we talked about this, right? Back at the beginning of section 11.1. And you don't have any real way of talking about a limit at this stage with factorial. So you can't even do the divergence test here, okay? So you have two options. You can just dive right in with writing out some partial sums, or you can try to simplify that expression a little bit if you want, okay? So let's just do that just to make sure you can understand working a little bit with factorials and without numbers, right? Factorials with letters, right? Okay, so our numerator up there is n, right? And what does n plus 1 factorial mean, right? I'm going to multiply 1 times 2 times 3 times 4 times 5, blah, 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 up until I get to n plus 1, right? Or I'm going to start with n plus 1 and keep taking 1 away and keep multiplying that until I get down to 1, right? So there's really a hidden factor of n in here, right? Because n plus 1 is just n plus 1 is the very first guy that gets multiplied, and that's going to multiply times n factorial, right? That we did that kind of like 5 factorial is 5 times 4 times 3 times 2 times 1, which is 5 times, what is that? 4 factorial, right? Okay, so n plus 1 factorial is n plus 1 times n factorial. Okay, well, again, what is n factorial then? So I got an n on top. I've got an n plus 1 here now. How can I write n factorial? Good. N times n minus 1 factorial, right? Yeah? 5 factorial is 5 times 5 minus 1 factorial. Yeah? Another way to think about it. Good. Okay, so I could, if I wanted, right, cancel these two n's right here and say that this is the same thing as the sum n equals 1 to infinity of 1 over n plus 1 times n minus 1 factorial. Yes? Okay. So, all of those things are the same thing. So that's just good to pay attention to as well. We're going to have a lot more work with factorials coming up. Let's look at some partial sums. Okay, so let's look at S1. Now this guy starts counting at 1, so S1 is just our first term when n is 1, right? Depending on which one you want to look at, right? If we look at this version, right, we have, if n is 1, we've got 1 over 2 factorial, right? Okay? You know, maybe we'll just do it, you know, if we look at the other version, that one, what do we have? S1 is 1 over 2 times 1 factorial, right? Yeah? Does that make sense? You good? When n is 1? Oh, it does make sense. 2 times, when n is 1, 0 factorial, right? What is 0 factorial? Good, defined to be 1, right? Excellent, very nice. We talked about that before. So this is 1/2. This is also 1/2, right? Because it's, what is 2 factorial? 2 times 1, right? We'll have fun with factorials, yes? 1/2. Okay. All right, so what about S2? Well, if we do it this way, what do we have? Right, we've got 2 over 2 plus 1, which is 3 factorial. Let's write down our other guy first, right? S2 is what? The previous sum, which is 1/2, right? Plus the next guy when n is 2, right? When the next guy when n is 2, we'll get 2 over 3 factorial. Yeah? Okay? Whereas if we're doing it from that formula over there, we would have S2 is 1 over 3. 2 plus 1 is, no, I did that again. But be careful, don't do that, right? Trying to make this video end in a reasonable amount of time. So what is S2? It's the previous sum, S1, right? 1/2, plus the next guy, which will be when n is 2. So for that one, it would be 1 over 2 plus 1 is 3 times 2 minus 1, 1 factorial. What's 1 factorial? Also 1, right? Okay. So here we've got 1/2 plus 1/3, right? And here you also have 1/2 plus 1/3, right? Because if we write out what 3 factorial is, it's 3 times 2 times 1, right? And these guys cancel, right? It's just exactly what we did up there, but in general. Yeah? Okay. Okay. Let's see. Let's do one more, and then I'll let you just have more fun with this. So let's do S3 this way, okay? So if we go with this formula right here, S3 is the previous sum plus the term when n is 3, right? So the term when n is 3 would be 3 over 3 plus 1, which is 4 factorial, right? If we do it over here, and use that formula, what is S3? The previous sum, which is 1/2 plus 1/3, right? Plus the term when n is 3. When n is 3, what would we have? 1 over 3 plus 1 is 4 times 3 minus 1, 2 factorial, right? Which is precisely what the other guy is as well, right? So here we have 1/2 plus 1/3 plus 3 divided by 4 times 3 times 2 times 1. That's 4 factorial, right? And so what do we have there? 1 over 4 times 2 factorial, which is the same as that, right? And so that is 1/2 plus 1/3 plus 1/8. Yeah? Okay, so either way we have the same things. Now sometimes it helps to not add stuff up right away, and sometimes it helps to add stuff up as to try to see a pattern. So let's just try to add these for a sec. So what really is S2 then? What's 1/2 plus 1/3? Okay, right? We need a common denominator, which will be 6, right? 3 over 3, right? So we'll have 3/6 plus 2/6, right? So if we multiply this guy by 3 over 3, and multiply this guy by 2 over 2, right? Then what do we have here? 6, 3 plus 1 is 5. Yes? Okay. So we have 1/2, 5/6. Then what do we have here, right? Well, here we've got 5/6 plus 1/8. Yeah? What's our common denominator there? Good, 24. And so if I do 4 over 4, multiply this guy by 3 over 3, right? What do I have? I've got 20 plus 3, which is 23 over 24. Yeah? Okay? All right. You can do S4. You should do S4 for yourself, right? And the goal is to see if we can come up with a formula in general for S sub n, right? So let's just remember our factorials. 1 factorial is 0 factorial is 1. 1 factorial is 1. Good. 2 factorial is good. 2. 2 times 1, right? 3 factorial is 3 times 2 times 1, right? Which is 6. 4 factorial is, right? 4 times 3 factorial, which is 4 times 6, which is 24, right? Anybody seeing those numbers anywhere? Yeah. Okay. Right. So we got 24 and the 6, right? The 2 there. Okay. Okay. Maybe. Yeah. Do you see it? Do you see it? Okay. And then how does the numerator relate to the denominator? How does the numerator relate to the denominator? How does the numerator relate to the denominator? Think about that. I won't finish it. I think you're pretty much there, right? Yeah. What does this turn out to be? 5 times 4 factorial, 120. If you do the next one, you may see that guy pop up in the denominator, right? It's always good to have these numbers in your head because those factorials come up as well. I'll let you finish that guy out and see what you think. See if you can come up with then a formula that you can then try to manipulate so that you can then decide if this series is convergent or divergent, and if it converges, what would it converge to? All right, that's it for today. I have no idea how long this one is, guys, but I will look forward to seeing you next time on Math 236 at Home Edition.